Next, let's discuss another concept called a class. What is a class? To put it simply, it allows us to define an object which can contain various attributes or potentially many other objects. Within it, I can also define its inherent functions or methods to modify it. That is what a class is. For example, take bananas and pears. Apples all belong to the fruit category. So we can define a fruit class and then define its variety or its price. Now, let's define a dog class as an example. Let's copy this code over. Alright, the definition is complete. Now, let's walk through the definition process. When defining it, this is our class name. This line defines the properties, attributes it possesses. And this part defines one of its functions. When defining properties, note that there are two underscores here, not just one. With only one underscore, the code will not run. The self keyword represents the instance of the class itself. When we proceed with the definition, we need to define its name and age. As for the price, 100 is set here as the default price. It will be updated once a new price is provided. Now, looking at the part below, you see this function follows the same logic. Self represents the instance itself. To change the dog's name to a new one, we use nameFetchChange, where the formal parameter is the new name. This will replace the original name with a current one. Now, let's see how this works in practice. We'll name this instance cat. Instantiating it as a dog object, we'll set its name attribute to cat and set its age to 1 year old. And its price is 1,000 yuan. And just like that, we have defined the object. That is cat, which is an instance of the dog class. So now, let's try to print out the output. As for its name, you can see that the name is cat and its price. You can see that the price is 1,000. Now, if we want to change its name, right, to change the name, we use cat name FetchChange. Then we enter the new name here. For example, let's name it Bubby. Now, let's output its name again. Then you can see its new name is Bobby. The class is a key concept that we need to master, because later on it will involve Abaqus's root objects. These objects actually involve various aspects of the software's functionality. Let's briefly mention it here in Abaqus. There are 3 root objects we need to understand. They are the MDB model database, and the ODB output database. It is indeed the output database. There is also a display root object session. Regarding these, our focus is to understand MDB and ODB, as they are crucial for subsequent parametric modeling and results export. They play a major role in analysis. As for the session, we'll mention it when the time comes. This part of the content still needs to be digested. You can also go online to learn more about other features of a class, such as inheritance and polymorphism. I won't cover those here because we don't actually use this very often in our own scripting. I am just giving you a quick refresher to provide a basic understanding, just so you are aware that these concepts exist. As for a more in-depth study of this topic, you'll need to explore that further on your own. Next, let's discuss what we mentioned previously regarding the Abaqus root objects. Specifically, we are talking about the ODB root object. The ODB is primarily a database designed for carrying out post-processing on the results. It contains several branches underneath, which are the assembly, then the instances, and the steps. Under the assembly, there are instances, which also include node sets and element sets. Then, under the step section, there are the specific increment steps. Within the field output results, there are detailed data entries under specific field outputs, such as the output for strain, stress, and so on. This part is the history output. Under history output, there are also certain results, including energy data. Before we proceed with the ODB root object development, we need to first create a model. For instance, let's start by building a model from scratch. We can take a look at how to construct a model. Suppose we create a rectangle with a length of 50 and a width of 30. And then we place a circle in the center of it. In this case, we set its thickness to 20. Actually, 20 is a bit too much. Let's change it to 10. Now, regarding this model, let's take a look. We are going to assign a material to it. For example, structural steel. Density is 7.65 E -9. The Young's modulus is 210,000. Poisson's ratio is 0.3 here. Then uncheck this option. There's no need to have it created automatically. We establish a static general analysis step. Create the field output, since we will be performing post-processing later. For post-processing, the information we need to extract must be configured in the field output first, because we must set it up correctly to obtain the desired calculation results. Without these results, we wouldn't be able to perform any post-processing. Note that for this part, we will use nodes and then for the settings below. Let's modify the section below. We'll output stress and strain E. Let's just output E. Then P, Q, and displacement U. And we'll output misses stress. We don't need the rest. We'll mainly focus on these few variables. It is important to note that if you are using an older version of Abaqus, you might not be able to select this option here. Another important point to note is that for stress and strain data, by default, the stress and strain data is initially displayed at the integration points. However, what we want to do now is to extract these results from the nodes if this specific section is missing in your version of Abaqus. Then we will need to modify the settings via the keywords later. I'll explain how to do that in a moment. Now, why are we using nodes here? Because during the subsequent post-processing, we will output data by either defining a set for these nodes or selecting the nodes directly for output. Let's save it like this. We'll leave the history output as it is. As for the keywords, what should we do? Right here, we have the keywords editor. In here, let's take a look. Regarding these output settings, it should be right around here. Yes, look at this section. In this part, originally, if we had set this as a field output, and if we had set the position to integration points, then what would be displayed here? It would display element output here. Now, if we change it back to nodes, let's take another look. It will change accordingly. For those who might be using an older version of the software, we can go directly into this section and make a modification directly within the keywords. There is one more thing to keep in mind, which is that when we set up the output, we must ensure the increments we want to output are consistent with what is actually recorded in the result file. The output frequency must be consistent. Why is that? For example, if it is set to output at every increment, then every increment will have a corresponding result. Then, as long as it is within that step, I can extract the data from any of those increments. However, if I only output every 2 increments, then after the first one is recorded, the second increment will have no data. Consequently, in post-processing, there would be no way to export results for that second increment. So this setting determines exactly which increments is valid information, can be extracted during post-processing. This is also something you need to pay attention to.
Focus on various issues in finite element analysis. For more related professional knowledge, please follow my YouTube channel or click on the relevant links of each video to learn.